Okay, this is a follow-on to our most recent video on model calibration. Now that you know the basics of model calibration and how to consider error norms and both flow and head observations, etc., the next question is, how do you do this in GMS? What tools are provided in GMS to assist you in the calibration process? And there are a lot of tools we can use, some very powerful tools to help you quickly get a feel for what your errors are looking like and how close you are to a calibrated model. The first thing is something that we call observation points. These are used primarily for monitoring wells. Theoretically, you could have observed concentrations for a contaminant transport model, for example, but typically it's heads associated with wells. And so this is coverage in the map module. We sometimes refer to this as an observation coverage. Basically, it's a coverage containing a set of points where each point is an individual monitoring well that has either one observed head value or a whole series of observed head values over time, depending on if you're doing a steady state or a transient model. So to create an observation coverage, you just create a new coverage, and then over on the right column there's this observation points set of attributes. Just make sure you turn on either head or transient head, and the other ones are a little less important. And then down on the bottom there's a really important one, 3D grid layer option for observation points. When you create some observed head values at a specific XY location, if you have a multi-layer model, you need to be able to designate what model layer those observations are associated with, and you can do that either by entering the layer number or by using the elevation of the observation point. You can assign an elevation to individual observation points, or you can assign a well screen, and then it'll automatically determine it from the well screen. The default option is by layer number. And if you're doing a one-layer model, that's all you need, and it's just going to go into layer 1. So once you create an observation coverage and enter a series of observation points, this is what the attribute table is going to look like. This is very similar to, again, a point feature class in ArcGIS, if you're familiar with that. Each observation point has a name and an X, Y, and Z coordinate. In most cases, you can ignore the Z coordinate unless you're using that to determine what layer it's in. In this case, we're using the layer number option, so this column right here tells it what layer to put the observation in. You can toggle the point coordinates on or off if you want. And then we have the observed head. These are the values you observe in the field. And then there's an observed head interval and a confidence. The default confidence is 95%. I would recommend that you leave it that way. And then the observed head interval, this is like your calibration target. So 1.5 would mean we want the heads to be, the computed head to be within 1.5 meters up or down of the observed head. That's one way to think of that. And you'll see we have some different numbers there. The interval and the confidence are then used to calculate a standard deviation, assuming a normal distribution. And that's just from basic statistics theory. You can look up the equation for that if you like. And then that standard deviation, the weight that's used to calculate the sum of squared weighted residuals or the weighted error norms, is 1 over the standard deviation, or 1 over the standard deviation squared. And of course, if you put in just a uniform head interval for all your points, then they're all equally weighted. And unless you have a strong reason to do otherwise, that's what I generally recommend you do. And then in this case, the user has already run the model and read in the solution. And so it shows the computed heads in the second to last column, and then the last column is the residual. And so if you take the observed head minus the computed head, it gives you your residual. And let's see, I think this might be from an earlier version of GMS. Where it's computed minus observed. These signs on this probably need to be flipped to use the current ModFlow sign convention of observed minus computed. But this is how the attribute table is laid out. And of course, you can use this to change your intervals or just view your individual results either way. That's how you manage your observation points. So how do you get these into GMS? You can organize them in a spreadsheet if you want, or just in a flat text file. If you save them to either a .txt file or a CSV file, it lists TXT file here, but a CSV file works as well. And then you can open them using the text import wizard. Or if you have them in Excel, you can just copy and paste your table of values, copy it in Excel, and then paste it into GMS, and it will launch the text import wizard. A lot of these fields are optional. The only ones that are truly required are X and Y, and the head field. You can manually enter the other values in this table once you've added them, if you like. But you do have to at least have X, Y, and head values as you import those. So it's a very easy process. You just it's this text import wizard is you just access it with the file open command. You do file open and select the file, and then there's the same kind of wizard we saw with the scatter point options. And you tell it what kind of file it is, an observation file, and then designate what each column represents. And we'll go through that when we do our exercise in class. Another important part of this is calibration targets. So let's suppose I have an observed value. These are little symbols that are plotted on each observation point in the main GMS window once you've entered your observation points and then read in a model solution. In this case, the computed value is above the observed value, so there's a little green bar that shows the magnitude of that. That whisker plot, as we call it, the size of that is a function of the interval that you input right here. So that, let's suppose this was 2 meters, then this would be plus 2 meters and minus 2 meters, so a 4 meter range. And whether you have a negative or positive residual, it would be within that range. And that gives you a quick feel for how close your error is to the observed, how close your computed value is to the observed value. Furthermore, if you are within the target, it's shown in green. If you're outside the target, so greater than 100% error, where that 100% of the interval, you're outside of that interval, either on the positive or negative side, it's yellow. And if you have more than 200% error, it's shown in red. So as you look at these displayed on your map of your groundwater model, and you look at the greens and the yellows and the reds, you can get a really quick, intuitive feel for how your calibration error is spatially distributed. These are really useful tools as you calibrate a model. Another tool we often use is the calibration statistic plots. So if you click on the Create Plot macro, it brings up the plot wizard, and the very top item in the upper left here is computed versus observed data. And so what that does is it generates a plot that kind of floats over your main window. And for each of your observation wells, it plots the computed value versus the observed value. And if the computed and observed values are equal, then they fall on that 45-degree line indicated by that solid line in the middle. This is a very common way to show the results of a calibration exercise. In fact, I don't know if I've ever seen a groundwater model report that doesn't have this 45-degree plot in it. It's just an industry standard way to show how well your model is calibrated. So a calibrated model, each of these points that you see would be tightly grouped around that 45-degree line. And any deviation from that represents a difference between your computed or observed value, either on the high side or the low side. And so as you continue to calibrate your model, hopefully you see the spread of these points get compressed more and more closely around that 45-degree line. And it's just a nice intuitive way of representing the results of your calibration. In addition to observed heads, we have observed flows, and these are associated with things like streams and drains, and so they are assigned to arcs. You can also assign them to polygons if you're dealing with a lake or a reservoir. Typically we assign them to rivers and streams, and so in this case we have a river arc. If you double click on the river arc and you've turned on observed flow, so let me back up a little bit. If we go all the way back to here, over on the left side, if you scroll, it's not shown. If you scroll down to the bottom, there's a way to turn on observed flow as one of your properties on a source sink boundary conditions. And so if you do that, you can then assign the observed flow rate. And, a negative value would mean water is leaving the aquifer. The sign is always from the viewpoint of the aquifer. So a negative value would mean a gaining river. And then the interval should be about maybe 5% of the magnitude of that observed flow rate. And we talked about that last time, but that's a good rule of thumb for your observed flow interval to give it a good proper weight. Now, it turns out that sometimes, an observed flow is a gain or a loss in a stream. So it's a deviation in the flow rate. And in some cases, you have two gauges at two different locations along the stream, and the difference in the flow measured when you're not in a precipitation event would be that gain or loss. But in other cases, maybe your observation contains contributions from multiple stream segments or arcs. So part B, as for example, maybe this is all a groundwater fed stream and you just have one gauge downstream. Well, now you need to consider the input or the gains or losses for all of these streams, and you need to assign an observation to that set of arcs as a group. So to do that, we have an object called an arc group. If you select the individual arcs and then select the Create Arc Group command in the Feature Objects menu, it creates a new entity called an arc group. And then there's a Select Arc Group tool that you can use to double-click on that group and assign properties directly to the group as if it were a single arc. So that's how you handle cases like that. And then once you've assigned your flows either to individual arc or to an arc group, if you click on the arc or arc group in the main GMS window, you will see a display at the bottom showing the computed flow and the observed flow and also a residual. And the same is true when you click on an observation point. It will show you the computed and observed heads at the observation point as well. So you can explore your errors directly by clicking on the associated objects in the main window. Finally, if you want to look at your comprehensive error norms, or that represent the error for the total model, these are stored with the model solution. When you read in a ModFlow solution, it shows up as a folder and underneath your 3D grid. In this case, we have a solution called Calib, C-A-L-I-B. If you right-click on that folder and select Properties, it brings up this window that shows you your mean absolute, root mean squared, residuals, or error norms for both head and flow. And then you also have the second to the bottom list there is the sum of the squared weighted residuals. And so those are all really important to look at as you're calibrating your model. Obviously, you want to minimize everything, but that gives you a way to look at all of these different error norms. So we have a tutorial and exercises we can use to go through and illustrate how to use these, but now you've had a basic presentation on the main calibration tools in GMS.